So looking at chapter 16.5, we're going to be looking at the idea of surface area in 3D. So there's a couple different ways that we've looked at viewing surfaces and expressing them in the three-dimensional coordinate system. The first one that we've seen a lot of and we're very familiar with is the explicit way to do it. So the first one is explicit. And this is in the very familiar form of like z equals a function of two variables, like x and y. For example, it could be something like z equals x plus 2y. That's an example of an explicit surface because it's a function that's explicitly solved for the dependent variable. In this case, z is explicitly solved for. Now, an implicit surface might look like z plus 2y plus 3 equals 5. This is an example of an implicit surface. And they're related because you could easily solve this for z equals and get it into the explicit form. So there are two sides of the same coin in that sense. But the second big way we're going to look at is a parameterized surface. Now, we've had experience with this before in chapter 13 when we were talking about vector-valued functions and motion in space. And we did a lot of parameterization of lines. If you remember parameterization of lines, that's when we would solve a line equation in the form r of t equaled, some function in the I direction plus some function in the j direction, right? So it's that exact same idea, but instead of using one parameter, right, one parameter we used was t, usually, so that was the parameter. That gives us a line, if we only have one variable that we manipulate in that way. But if we add a second variable and do a parameterization in terms of two different independent variables, then that actually gives us a surface. So the way we write the parameterization of a surface is instead of r of t, we actually do r of u and v. These are kind of the standard placeholder variables, just like t is for a single variable or a single parameterization. We tend to use u and v for surface parameterizations. And so just like when doing lines or curves, you can have some function of u and v in the I direction, and you can have a different function of u and v in the j direction, and then a third function of u's and v's in the k direction. And so the combination and the manipulation of the u value and the v value in all three cardinal directions will give you a surface in 3D. So this traces out a surface every time. Very nice. So these are the two different ways that we're going to primarily look at expressing surfaces in 3 dimensions. And so one of the first ideas we're going to look at is the idea of finding the surface area of some of these. And so before we get into finding surface area of these different surfaces, let's first just have some practice parameterizing surfaces. So we did a lot of practice again in chapter 13 where we would give you the equation of a line and ask you to write the parameterization of it. So you would have to solve for the x value, maybe the y values in terms of t and the x values in terms of t, and then rewrite it in that parameterized form. We're going to be doing the same practice just now with two variables instead of one. So when I'm looking to parameterize a surface, one of the first things I need to do is to choose what coordinate system I'm going to use. And kind of a good insider tip for these two variable parameterizations is that we've learned a bunch of coordinate systems, right? And some of them translate really well to parameterizing surfaces in 3D. And you'll see some patterns in ones we use. So for this first one, we're going to find a parameterization of the described surface. So this first one is a paraboloid in the form z equals x squared plus y squared for all z values less than or equal to 4. So just as a reminder, this is really easy to sketch. We can just get an idea of what the surface looks like. So this is the paraboloid less than or equal to 4, so a height of 4. So we'll have the top of it here. Right, it's kind of this shape, where this is at the height z equals 4, and then you can find what the radius is on the bottom by using the z value is equal to the x squared plus y squared coordinate. So you know that the radius this traces out here is equal to a radius of 2. Oops. How do I undo that? Yes, so a radius of 2. Perfect. So that's the shape we're trying to parameterize. So let's set up our template where we'll have, in terms of 2 variables, is going to be equal to something in the I direction plus something in the j direction and something in the k direction. So that's kind of our blank template that we're going to fill in. So now we got to decide what are the u and v variables that we're going to substitute in. Now the trick for doing a lot of these parameterizations is that a coordinate system we already know that translates really well to these kinds of shapes is the cylindrical coordinate system. So you want to think with cylindrical coordinates. Oops. And so just as a brief reminder, the cylindrical coordinate system was the one which had the x value equal to r cosine theta, the y value is equal to r sine theta. If you remember, z is just equal to the z, right? So the z doesn't change. It's just the polar coordinate system with a height added. And then the last relation that we want to keep in mind is that idea of x squared plus y squared being equal to r squared. So these make up the translation equations for the cylindrical coordinate system. So let's see if we can apply that in this case. So we're looking to somehow turn this z equals x squared plus y squared into a function of just 2 variables, u and v. So right now it's in terms of 3. So we can use the cylindrical coordinate system to turn it into a function of 2 variables, where r is going to equal the u value and theta will be the v value. So we'll use cylindrical coordinates, and we'll let u equal r, and we'll let v be theta. So in that case, the x values go here. So x in that case, in cylindrical coordinates, right, x is r cosine theta, and y is always r sine theta. And now we just got to take care of z. So in this case, it's telling you that the z component is equal to x squared plus y squared, which we know from our translation equations that x squared plus y squared is always r squared. There you go. So now we wrote this equation that was expressed in 3 variables in terms of 2 variables, just r and theta. So I guess to be notationally correct, we should come in here and we should make these be r and theta instead of our u and v placeholders. The very last thing we have to do is we have to bound our parameters. So, we usually, when we were doing that in chapter 14, we would always bound t between 2 values so that we would have just the portion of the line or the curve we wanted. Same thing here. We only want the portion of this paraboloid that's below the height z equals 4. So the way we do that is we need to bound both r and theta. So in this case, we know that theta, right, like usual, goes between 0 and 2 pi, because we're getting the full rotation around the z-axis. And then to bound r, right, I kind of did that with my initial drawing. R just goes from 0 to 2. And that shadow casted on the xy plane gives you that portion that only goes up to a height of 4. So that's just between 0 and 2. So this right here would be the parameterization of this explicitly defined function. So 2 ways to express the same surface. Oftentimes it's easier to do the calculus with the parameterized form of the surface, and so that's why we're practicing translating into a parameterized version. Okay, let's do one more before we move on to the actual meat of this section, and we're going to be looking at, what was it asking us to do? Find a parameterization of this surface, the cone frustum. So this is a shape in geometry, and a frustum is just a portion of a solid that lies between two parallel planes, right? So a cone might look like this, and a cone frustum would be just the portion of a cone that would lie between maybe this plane and another parallel plane. So cone frustums are this kind of shape right here. Right, so it's just a truncated cone between two parallel planes. So that's all that's saying. Let's get rid of that for some more room. So in the first octant, so that's really important. So that's going to limit how much of the cone we're actually getting in the theta direction, right? So the first octant portion of the cone z equals the square root of x squared plus y squared divided by 2 between the planes z equals 0 and z equals 3. So that is going to look something like, when z equals 0. Oh, so when x equals 0, y equals 0, you get a height of 0. Okay, so it's a portion of a cone. This actually might not be a frustum. Between 0 and 3. So we want the top of it to be a 3. And the bottoms here is equals 0. And then the sides of the cone are going to be given by the relationship the square root of x squared plus y squared divided by 2. So it will look, yeah, something like that. Where, let's see. So if this is at a height of 3, let's come back to this in a second. Let's start doing our setup. This one's a little bit trickier. So let me just start with my blank template. Now again, for a lot of these, you're going to be using the cylindrical coordinate system because it really easily sets up 3D surfaces in terms of two variables, r and theta. So I'm just going to get that started here. So we'll start with a parameterization in terms of r and theta with an I component, a j component, and a k component. Okay, and we know, like usual, in the cylindrical coordinate system, x is always equal to r cosine theta, and y is equal to r sine theta. And now we just got to figure out this k component, what the z component is. So here we have that z is equal to, what is it, the square root of x squared plus y squared divided by 2, which when we apply the cylindrical coordinate system gives us the square root of r squared divided by 2, which would just be r halves. So r halves is what goes in for the z component. That's pretty easy. And now we know that we need the height of it to be less than 3. So how can we do this? I see. So we can bound So we know r halves, right? So the z component, right, in our parameterization has to be between 0 and 3, right? That's what that last part said. And now if we just multiply out r to get r by itself, we know that r has to be between 2 times 0, which is 0, and 2 times 3, which is 6. Okay, cool. So this radius down here would actually be 6. So it's definitely not drawn to scale. It's much wider than it is tall. It's twice as wide as it is tall. And now, this part that I highlighted, my drawing's actually wrong. The first octant portion of the cone, which means that you just want the portion from the x-axis to the y-axis. So just this eighth of the cone. So really, it would be kind of this cut out. I guess it's a very thin slice of a cone. So you would bound theta, of course, to get just that first octant, would be between 0 and pi halves. So this parameterization, along with these bounds, gives the correct surface parameterization. Okay, perfect. So now we're going to look at the calculus portion of this, which is applying double integrals to find surface areas of these parameterized or explicitly defined surfaces. And so, just like we had two ways of expressing surfaces, we also have two corresponding formulas for finding the surface areas of different portions of these surfaces. And so this one right here is, obviously this one is used for parameterized surfaces, because it's in terms of u and v, those two parameters that you would write it in. So this is for parameterized surfaces. And then this one is for explicitly solved surfaces. So one of the first things you need to do is, if you're asked to find the surface area of some surface, is first identify whether you're working with a parameterized surface or an explicitly defined surface, and that will let you know which two of the surface area formulas to go and apply. So in example 2, it's asking us to find the surface area of another cone frustum, which is the portion of this cone between the plane z equals 1 and z equals, pi thirds. So the first thing to do is decide whether or not you're working with a explicitly defined surface or a parameterized surface. Now, you can translate between the two. Oftentimes, one is easier to do than the other. And in this case, because it is a circular in nature shape, right? It's a portion of a cone. So, right, we're going to be working with a shape that kind of looks like this. Right, a cone frustum. We know from previous chapters that oftentimes when your surface or your shape in 3D is circular in nature or cylindrical or kind of conical, then using that cylindrical coordinate system makes a lot of the math, the calculation, and the simplification a lot nicer and cleaner. So knowing that ahead of time, and that's definitely something that just comes with experience, I know that this problem is going to be easier if I first apply the cylindrical coordinate system and rewrite this is a parameterized surface. So the first thing I'm going to do here is parameterize this surface. And this is going to be similar to the example we did above. And so I'll get r in terms of r and theta. And we know that the x value in cylindrical coordinates is r cosine theta I plus r sine theta in the j direction plus, and now we just need to solve for the x value, which is of the square root of x squared plus y squared divided by 3, which if you do the same simplification we did earlier, that just comes out to r thirds in the k direction. And we want the portion between 1 and 4 thirds in the z direction. So if we do the exact same method for finding that, we know that our thirds has to be between 1 and 4 thirds. So if we multiply out the 3 to either side of the bounds, you'll get r needs to be between 3 and 4. And then theta, right, we want the whole cone frustum, so that'll just be between 0 and 2 pi. Now, one of the confusing parts that a lot of students will ask is when we're doing these surface area problems, right, you might imagine that this is where this surface lies, right on the xy plane, between a height of 1, and then this would be like z equals 4 thirds, just for example. When you're finding the surface area, you're just evaluating the surface area of the sides of this shape. Right, so it's just the part around the sides here. You're not including the base and the top. So you're not including this portion that lies up here. That's not included in the surface area, and similarly the base is not included in the surface area. And this is reflected in the r bounds. So in the bounds of r on the xy plane, you know that they only go from r equals 3 to r equals 4, which would be this portion that goes from like r equals 3 to r equals 4, which is the shadow of this shape on the xy plane if you imagine the top and the bottom to be hollow, right? So that would give you kind of this shape here for the r bounds, which makes sense. If you were to shine a light, shine a light down here from the top, the shadow it would cast on the xy plane would look like the r bounds, which is exactly what it should be. So that means that we set up the region right, and we set up the bounds on our parameterization right, because r does not include the base and the top. Otherwise, it would be fully closed in, if that makes sense. Okay, so we have all the setup. Now we know that we're using a parameterized surface, so we're going to use our parameterized equation, this version here. The double integral over the region, where the integrand is the absolute value of the cross product between the two partial derivatives in the u and the v direction. So let's apply that down here. So first we're going to find the two partial derivatives to use in the integrand. So we'll find the partial derivative of this parameterization with respect to r, and we'll find the partial derivative with respect to theta. So that's what we'll do next, just so we can take the cross product to put here as the integrand. So the partial derivative with respect to r, and remember, when we do the derivatives of vector valued functions like this, you just do it component by component. So it's the r partial derivative of the I component added with the r partial derivative of the j component, and so on. So it's just component by component. So doing this real quick, we would get that it is just cosine theta in the I direction plus sine theta in the j direction, and then the partial derivative of r thirds would just be 1/3 in the k direction. So that's just 1/3 k. So we found our r partial derivative in the r direction, and now we just need the corresponding theta one. So in that case, we're going to get, negative, right, that's negative r sine theta. Let me just make sure cosine. Yeah, negative r sine theta in the I direction, plus r cosine theta in the j direction plus 0k. Okay. There you go. So now we have our two components that we need to take the cross product of, right? So we're finding this integrand first. Now we need to cross them and take their magnitude. So let's do that real quick. So if we do the cross product of our r with our theta, I'll let you do this calculation on your own, but it does come out to be negative 1/3 r cosine theta I, all of that in the I direction, plus, minus, I have my work from earlier in front of me, minus 1/3 r sine theta, all of that in the j direction, and then there is just r in the k direction. Okay, so that's what you get for the cross product, and now we just need to take the magnitude of the cross product, which is just going to be the square root of the sum of the squares of all these, which is the square root of, so we square each of these components and add them together. So that'll just be 1/9 r cosine squared theta plus another 1/9 r sine squared, and you might see where this is going to simplify nicely, plus just r squared. So that's the square root of the sum of the squares, and easily you can see the Pythagorean identity hidden in there. So we have that if you factor out a 1/9 r from both of these first two terms, then you just get r9 times 1 plus r squared. Oh, I'm sorry. All these r's should be squared as well. That's why it wasn't going to simplify. So yeah, so it should be 1/9 r squared cosine squared. 1/9 r squared sine squared plus r squared. Right, so that gives us r squared ninths times 1 that you get from doing the cosine squared plus sine squared, plus the r squared at the end. And that's the same as just 9 r squared ninths. So now you can add them together, and you'll get the square root of 10 r squared ninths. There you go. So it simplifies relatively nicely. So now I'm just going to finish the rest of the setup and leave the evaluation to you as an exercise on your own. But anyway, now that we have all the components, we can fully put in the form of this first surface area equation. So we get area is equal to the double integral of the square root of r squared ninths, or 10 r squared ninths, r dr d theta, r dr d theta, because we're in cylindrical coordinates. And now the bounds on r and theta have to be between 3 and 4 and 0 and 2 pi. And that's what we established up here at the top for our bounds on r and theta. Now if you're looking for the answer to check your work, the answer you're looking for the surface area of this shape is 7 pi square root of 10 over 3. So that's what the evaluation comes out to be. Now let's look at one more example. Find the surface area of z equals xy that lies within the cylinder given by x squared plus y squared equals 1. So let's get an idea of the shape we're working with here. So I'll just draw some coordinates real quick. So it's the surface x squared plus y squared, which is that kind of saddle-shaped surface that comes up in this direction. Whoops. How do I go back? I'm getting rid of too many of my axes. Whoops. So it's the kind of weird shape that comes up in this direction and then up in the and down in these quadrants. So back there it goes down and it goes up behind. So when x and y are both positive, it's increasing, and when x and y or one of them's negative, it's decreasing. And then over here in quadrant 3, where they're both negative, it's also increasing. So it's kind of this saddle shape. And we want just the portion of it that lies within the cylinder x squared plus y squared equals 1, which would just be kind of the unit cylinder of radius 1 that kind of cuts out a portion of it there. So that's kind of a quick and dirty sketch of the surface we're trying to find the surface area of within that region. So let's get rid of that real quick. So since I already did an example using the parameterization method, let's do one to show the explicit surface method, where we apply this second formula for explicitly defined surfaces, and show that it's just as valid of a method to use. So in this case, this is already written in the explicit form. So this is Right, so that is the explicitly defined surface. And so, let's see, the area is equal to the double integral over the region of integration, where it's the x, what was it, the x partial derivative? Yeah, f of x squared. Whoops. So it's the x partial derivative squared plus the y partial derivative squared plus 1. And then it would be dA. So that's the formula we're trying to fill in. Let's get our components real quick. So first we'll find our two partial derivatives of this surface, right? So that's pretty easy. So fx is just equal to y, and fy is just equal to x. So now we can put in to our working equation. We'll have two double integrals that we need to bound here in a second, where the integrand is just x squared plus y squared plus 1. And then we'll do dA for now. Okay, so let's get some bounds on it real quick. We know that the sides of the shape have to lie within this cylinder, x squared plus y squared equals 1, which is just the unit circle as a cylinder. So you know that the radius is going to be between 0 and 1, and then we want the full rotation, like the full shape, so that'll just go between 0 and 2 pi. So that's pretty easy to set up those bounds. And now, because we used r and theta for bounds, right, we know that this dA has to be r dr d theta, because we just went into a polar coordinate system to do our bounds. So in that case, x squared plus y squared also needs to be converted into cylindrical coordinates as well. So that x squared plus y squared can be simplified just into r squared. So then you get r squared, the square root of r squared plus 1 times r dr d theta. And then if you do that integration, you'll get the surface area of this shape is equal to, let me put the answer in red, 2 pi thirds all times 2 raised to the 3 halves minus 1. So that's the answer you're looking for when you do the evaluation. But that is 2 examples, one applying the parameterized version of finding surface area, and another one using an equally valid version of the explicitly defined surface area evaluation. And so just to recap, this whole chapter was only about finding the surface area of different surfaces in 3D, and we revisited the 2 ways that we could define the surfaces, those being the explicitly formed surface and also the parametrically formed surface, where the parametric equation is of 2 different variables.